We are now going to briefly talk about orientation. Since our goal is Stokes' theorem and vector analysis, we will take a very utilitarian approach to this and defer some of the details and working out many of the equivalent ways of characterizing orientability of a manifold to a future course on smooth manifolds. First, let's define the orientation of a vector space. Definition. Let V be a finite dimensional real vector space. An orientation, or before I give that, let me just talk about equivalence. Let two ordered bases of V are said to be equivalent if the change of basis matrix from one to the other has a positive determinant. There are precisely two equivalence classes under this equivalence relation. That this is an equivalence relation is very easy to see. Precisely two equivalence classes. An orientation of V is a choice of the equivalence class. So orienting a vector space is rather simple. You just choose one collection, one ordered basis, and deem that to be the orientation. You can do that. Now this is related to what you would have already seen when you studied the vector cross product and so on. The orientation of a one-dimensional space essentially tells you direction. Which direction? There are only two possible. Take a vector space in the real number. Just take the real numbers. There are two natural bases: the set containing +1 and the set containing -1, and you can see that these two are going to be representatives of the equivalence classes. So that sort of determines which the positive direction is and which the negative direction is. Now in R2, choosing the orientation is like choosing which is clockwise and which is anti-clockwise. So if you have R2, if you choose E1, E2, this pair as the ordered basis, it sort of tells you that this what we call the anti-clockwise direction is the positive direction, and the other choice would be E2, E1, that's sort of determining the clockwise direction. The orientation determined by that is the clockwise direction. Similarly, in R3 you must have been taking your right hand and putting the index finger and the middle finger along two basis vectors, and the direction of the thumb gives you the positive thing. So it is sort of determining the screw, which direction must you screw a threaded screw for it to get screwed. Okay, so this is sort of like called screw rule or the thumb rule or whatever. It's some sort of ridiculous thing, but essentially the definition of orientation I have given now is just an extension of these basic things that you have already seen when you studied basic vector algebra. Okay, now there are several exercises on orientations in the notes. You must solve all of them. They are really basic. As I said, much of the details are going to be done in a later course on smooth manifolds. Now we are going to define orientation of a manifold. An orientation of a manifold is just orienting each vector space of the manifold. but we want to do it in a consistent manner. It shouldn't happen that when you break up the manifold into pieces, there are some drastic changes in the orientation when you move slightly. So this is to ensure that there are no drastic sign changes when you do the integration process for a form. So the orientation of a manifold is defined as follows. Orientation of a manifold, it's defined as follows. Let M be a manifold. We say M is orientable if we can find a collection of parameterizations phi from ui to m, I running through n, and of course ui subset of Rn are open. You can find a collection of parameterizations such that first of all the images must cover M. So when you take the union of all the phi ui, you must get the whole manifold M. And the second property is the following. The frame fields determined by any two such parameterizations must be equivalent if the images overlap. So the basic idea is the following. You have this manifold M. Let's say you have two different parameterizations near a particular point A. Now, what were the frame fields? Well, you just choose the standard basis here and just push forward under, let's say, d phi 1, d phi 2. Push forward these vectors. They will give you two different bases of the tangent space at the point A. These two bases should always be equivalent. Okay, so that this just sort of says that there is a consistent way of choosing these orientations throughout the manifold. Now, such a collection of parameterizations is called a orienting cover. Such a collection of parameterizations is called an orientation cover. So the orientation cover sort of determines the orientation of the manifold. It gives you how to orient each tangent space. What you do is you just push forward the basis vectors, the standard basis vectors in that order. Okay, that is important. You push forward E1 to En in Rn in that order. You will get a basis for the tangent space that is supposed to give you the orientation of that particular tangent space. So the definition is essentially saying that you can do this choice in a consistent and smooth way. Okay, now it turns out that not all manifolds are orientable. The famous Mobius band is not orientable. It has two sides. There is no way to consistently choose a basis for the tangent space of the Mobius band. Also, there are precisely two orientations that you can give to a connected manifold. That means that if you fix the orientation of one particular tangent space, the entire orientation of the manifold is determined now entirely. I'm going to leave it to you to show this as an exercise. Okay? And you can also characterize when a particular collection of parameterizations is going to be an orientation cover. That will happen precisely when you take two such maps phi I and phi j and look at phi I inverse of phi j, then the derivative of this map should have positive determinant. This also is going to be left to you as an exercise. Okay, so as I said, this is just a brief utilitarian treatment of orientation so that we can get on with the general theory and prove Stokes' theorem. There are many equivalent ways of characterizing orientations. For instance, for surfaces in R3, being orientable is same as being able to choose a normal vector in a consistent, smooth manner. And for higher dimensional manifolds, manifold being orientable is same as the existence of a top degree form that does not vanish anywhere. So all such equivalent characterizations and details are going to be left for a future course so that we can now proceed quickly to the general theory and prove Stokes' theorem. This is a course on real analysis and you have just watched the video on orientation.